Ever wondered what emulsions are and how they work? Well, let's embark on an intriguing journey to explore emulsions, a cornerstone concept in the world of pharmacy. Emulsions, in their simplest form, are a mix of two liquids that typically don't mix, like oil and water, but with a little bit of science and some stirring, these two can be made to coexist in a stable, homogeneous mixture. Now, why should you care about emulsions? They are everywhere around us, from the creamer in your coffee to the lotion you apply on your skin. More importantly, in the realm of pharmacy, they play a crucial role in drug delivery, enhancing the effectiveness of medications. Today, we'll be diving into the various types of emulsions, the theories behind them, their formulation aspects, and much more. So buckle up. Stay tuned as we delve deeper into the fascinating world of emulsions. So, what exactly are emulsions? Well, let's dive into this fascinating world. Emulsions are systems of two immiscible liquids, meaning they don't naturally mix. One of these liquids is dispersed in the other in the form of tiny droplets, creating a stable, homogeneous mixture. Imagine a vinaigrette salad dressing. Oil and vinegar don't mix, but a good shake disperses the oil into tiny droplets within the vinegar, creating an emulsion. Now, there are two main types of emulsions: oil in water and water in oil. Let's break down what this means. In an oil and water emulsion, the oil droplets are dispersed in a continuous phase of water. It's like a crowd of oil droplets having a party in a big room of water. This type of emulsion feels wet and cool when applied on the skin, which is why they're commonly used in moisturizing lotions and creams in the pharmacy industry. On the other hand, water and oil emulsions are just the opposite. Here, the water droplets are the ones having a party in the oil room. These emulsions feel greasy and are less easily washed off, making them ideal for products like ointments and heavy-duty moisturizers. And it's not just about lotions and creams. Emulsions play a vital role in many areas of pharmacy, from providing a method to administer poorly soluble drugs to improving the taste of certain medicines. They're also used in the food industry, cosmetics, and even in oil recovery. But how do we get these two immiscible liquids to mix? That's where emulsifying agents come into play. They act like peacekeepers, reducing the tension between the oil and water, allowing them to coexist in harmony. With this foundation, we can now explore the theories behind these intriguing mixtures. How do these peculiar mixtures come about? Let's explore the theories. Emulsions aren't just whims of nature, they are a result of specific scientific principles. Two of these guiding principles are the surface tension theory and the oriented wedge theory. Let's start with the surface tension theory. This theory proposes that emulsions are formed due to a difference in surface tension between two immiscible liquids. Take water and oil, for instance. These two don't naturally mix. However, when you introduce an emulsifying agent like a soap, it decreases the surface tension between the oil and water. This allows them to mix and form an emulsion. The oriented wedge theory, on the other hand, takes a slightly different approach. This theory suggests that emulsions are formed when the emulsifying agent orients itself at the interface between the two immiscible liquids, creating a type of wedge. This wedge helps to stabilize the dispersion of one liquid within the other, creating our emulsion. But why are these theories important? Well, they give us insight into the fundamental principles of emulsion formation. They explain why certain substances can be emulsified while others can't, and they guide us in selecting the right emulsifying agents depending on the substances we want to mix. Understanding these principles is not just for the sake of knowledge, they have practical implications in fields like pharmacy. For instance, many medicines are designed as emulsions to improve the absorption of drugs in the body, and these theories guide the formulation of such medicines. So the next time you see an emulsion, whether it's in your salad dressing, your skin cream, or your medicine, remember the science behind it. Emulsions aren't just fascinating mixtures, they are the result of meticulous scientific principles at work. Understanding these theories will help us grasp the next topic: formulation aspects. How does one create an emulsion? The answer lies in formulation aspects and emulsifying agents. Now let's dive into the nitty-gritty of emulsion formulation. Formulation is a crucial process that involves the careful blending of oil, water, and an emulsifying agent. Think of it like a culinary recipe, where each ingredient plays a specific role, and the proportions need to be just right. The oil and water form the two phases of the emulsion, while the emulsifying agent acts as the bridge that unites these two immiscible liquids. Emulsifying agents, also known as emulsifiers, are the true heroes of the emulsion story. These substances have the unique ability to bind both oil and water molecules, thanks to their amphiphilic nature. This means they contain both hydrophilic, water-loving, and lipophilic, oil-loving parts. By reducing the surface tension between oil and water, emulsifiers enable these two liquids to mix and form an emulsion. This is where the hydrophilic-lipophilic balance, or HLB system, comes into play. The HLB system is a scale that measures the degree to which an emulsifier is hydrophilic or lipophilic. Emulsifiers with a high HLB value are more water-soluble, while those with a low value are more oil-soluble. This system helps in selecting the right emulsifier for a specific emulsion type. The relative hydrophilic-lipophilic balance, or RHLB system, is another important tool. It's used to calculate the required HLB value for a particular oil phase. By using the HLB and RHLB systems, formulators can design emulsions with tailored properties to suit specific applications. So, as you can see, the formulation of emulsions is not a random process. It involves a deep understanding of the interplay between oil, water, and emulsifying agents, along with the smart application of the HLB and RHLB systems. Formulation is just the beginning. The real test is in the stability of emulsions. But that's a topic for another time. Until then, keep exploring the fascinating world of emulsions. Creating an emulsion is one thing, maintaining its stability is another. The stability of an emulsion, essentially, is its ability to resist changes over time. You've probably noticed that some emulsions separate into their individual components after sitting undisturbed for a while. This separation, or instability, is primarily due to factors such as temperature changes, the presence of impurities, or the applied mechanical forces. Now, how can we assess the stability of an emulsion? There are several ways, but let's focus on a few common ones. First, we have the creaming method. In this method, we observe the rate at which droplets of the dispersed phase move. A slower movement indicates a more stable emulsion. Second is the centrifugation method. Here, we expose the emulsion to high rotational speeds. If the emulsion remains intact, it's considered stable. Third is the heating-cooling cycle. We subject the emulsion to a series of temperature fluctuations. If it withstands these changes without breaking apart, it's deemed stable. Lastly, we have the freeze-thaw cycle. This is similar to the heating-cooling cycle, but involves freezing and thawing the emulsion. Again, an emulsion that survives this process is considered stable. These methods provide a snapshot of an emulsion's stability under certain conditions. Remember, a well-formulated emulsion should remain stable regardless of the circumstances. With a stable emulsion, we can now venture into more advanced topics. Let's take a step further into the world of microemulsions and self-emulsifying drug delivery systems. Microemulsions are clear, stable, isotropic mixtures of oil, water, and surfactant, frequently in connection with a co-surfactant. They are a fascinating subset of emulsions, primarily because of their unique characteristics. Microemulsions are thermodynamically stable, which means they won't separate into different phases over time. This stability, coupled with their ability to improve the solubility of poorly soluble drugs, makes them a valuable tool in pharmaceutical applications. Now let's switch gears to the self-emulsifying drug delivery system, or SEDS. As the name suggests, these are mixtures that use a specific balance of oils, surfactants, and solvents to spontaneously form an emulsion when mixed with an aqueous medium, like the fluids in our digestive tract. The fascinating part? This spontaneous emulsification process requires little to no energy input, making SEDS a highly efficient method for drug delivery. The importance of SEDS lies in its ability to enhance the bioavailability of drugs, particularly those that are poorly soluble in water. By utilizing the self-emulsifying property, the drug can be more efficiently absorbed in the body, leading to a more effective treatment. The realm of emulsions is vast and continues to evolve, offering endless possibilities. In this video, we've journeyed through the captivating world of emulsions. We've delved into their definitions and types, explored the theories surrounding them, and dissected their formulation aspects. We've also learned about the vital role of emulsifying agents and the intriguing systems of HLB and RHLB. But that's not all. We've also touched upon their stability, evaluation, and the fascinating realms of microemulsions and self-emulsifying drug delivery systems. We hope this video has shed light on the fascinating world of emulsions. Subscribe for more mind-blowing content.